Hello everyone. Our question for today is the following integral. Integral from 1 to infinity of ln of x over x squared plus 1. By the end of this video, you will see that this integral converges to a well-known constant. Alright, first of all, I'm going to apply this change of variable. So I'm going to let u equal to 1 over x. So this is the u, which is u prime times dx. And of course, we have to change the boundaries. And the integral becomes like this. Of course, here, since u is equal to 1 over x, then x is equal to 1 over u. So we replace x by 1 over u, as well as this x squared by 1 over u squared. And dx is this. Let's find a common denominator here. So it is 1 plus u squared over u squared. Or simply 1 plus u squared into 1 over u squared. So we get this integral. 1 over u squared cancels out with 1 over u squared. And I'm going to replace the ln of 1 over u by minus ln of u. So we obtain this integral. Let's cancel the minuses. Let us now interchange the boundaries and replace all the u's by x. And we obtain the following integral. Thus, our integral becomes equal to this. I will start solving this integral by applying the integration by parts technique. We let u equal to the ln of x. So of course, dv is the rest, which is that. For u, we find du, that's u prime dx. And for dv, we find an antiderivative of this. And of course, that's arctan of x. We then apply the integration by parts technique. So we multiply u times v minus the integral of v times du. So our integral becomes the following. So replacing x by 1 gives us 0. However, for the 0, we have to do the limit. So our next task is to calculate this limit. First of all, I'm going to write ln of x times arctan of x as ln of x over 1 over arctan of x. Why? In order to obtain infinity over infinity and be able to apply L'Hopital's rule, which is of course the derivative of ln of x, that's 1 over x, and the derivative of 1 over arctan of x, which is the derivative of the top times the bottom minus the derivative of the bottom, that's 1 over 1 plus x squared over arctan of x all squared. And of course, we can write it like this. Of course, this fraction is equal to this as well, which approaches to 0 over 0. So again, we have to apply L'Hopital's rule. The derivative of x is equal to 1. To find the derivative of the top, we have to apply the product rule. So it is the derivative of the first term, that's 2x, times the second, plus the first term multiplied by the derivative of the second. And that is 2 times arctan of x, times the derivative of arctan of x, which is 1 over 1 plus x squared. And this is what we get. Since we have a minus here, both terms become negative. These terms nicely cancel out, and this finally approaches 0 as x approaches 0 plus. So going back to our expression, this limit is 0, so we are only left with this integral. Alright, let us first recap what we have done so far. We started with this integral, we did a change of variable, we let u equal to 1 over x, so we ended up with this integral. We then applied an integration by parts for this, and we are left with that, which I'm going to call I. So our task now is to calculate this integral. First of all, let us take a look at arctan of x. We can write arctan of x as the integral from 0 to x of dt over 1 plus t squared. Let us apply long division for this fraction. So we divide 1 by 1 plus t squared. 1 divided by 1 is 1. Then I multiply. So we get 1 plus t squared Let us change the signs. So we are left with minus t squared. We divide again. Minus t squared divided by 1 is negative t squared. Let us multiply and then change the signs. Plus and plus. These guys cancel out. We get t4. Then t to the 4 divided by 1 is positive t to the 4. So we get negative t to the 4 minus t to the 6. We end up with negative t to the 6. So here it is negative t to the 6 and so on. So as you can see, the pattern is the following. 1 minus t squared plus t to the 4 minus t to the 6 plus t to the 8 and so on. So the exponents are even and the signs alternate. This means that we can replace 1 over 1 plus t squared here by this answer. And we get this. We then integrate both sides from 0 to x. This is of course arctan of x. And here we integrate term by term, so we get x minus x cubed over 3 plus x5 over 5 minus x7 over 7 and so on. And of course, this is the Maclaurin series expansion of arctan of x, but I just wanted to show you how to get it. Alright, the next step is to divide both sides by x, and then integrate both sides as well from 0 to 1. And that is our integral I. And this is clearly easy. So we end up with the following series. And this is a famous constant represented by g, which is approximately equal to 0.91596556, etc. It is called Catalan's constant, referring to the Belgian mathematician Eugène Catalan. There are so many more integral representations for this constant. Not only the 3 integrals that we saw in this video. There are actually more than 30 integral representations for this constant. For example, g is also equal to half integral from 0 to pi over 2 x over sine of x dx, as well as minus 2 times the integral from 0 to pi over 4 of the ln of 2 sine of x dx. It's also equal to the integral from 0 to infinity of arctan of e to the negative x dx, and also equal to the integral from 0 to pi over 2 of sinh inverse, or the inverse of the hyperbolic sine of sine of x dx, and really so many more. And that's all for this video. Thanks for watching and see you soon.